Hello everyone, my name is Ria and today I am giving my presentation on the topic chemistry of actinides. As we can learn in the chapter 1, F-block elements consist of two series of elements placed at the bottom of the periodic table. The two series of lanthanides and actinides which involve the filling of 4F and 5F subshells respectively. We have studied the chemistry of lanthanides in chapter 4. Let us now discuss the chemistry of actinides. Actinides. The 14 elements which follow actinium from thorium Z is equals to 90 to lawrencium Z is equals to 103 in the periodic table are called actinides. These are analogous to lanthanides and involve the filling of 4f orbitals. As in the case of lanthanide, the name of the series is after the name of preceding element actinium, with which these elements closely resemble. This is called actinions. Before 1940, only the naturally occurring actinides, thorium, protactinium, and uranium, were known. The remaining elements are made artificially by nuclear bombardment. These elements are also called man-made elements. Since these man-made elements have atomic number higher than 92, they are sometimes called the transuranium elements. Indeed, now man-made transuranium elements constitute about 15% of the known chemical elements. All the actinides are toxic to humans. These elements are radioactive and therefore the isolation and characterization of these elements, particularly the heavier ones, poses many problems. The individual elements are not produced cleanly in insolation but must be separated from other actinides as well as from lanthanides produced simultaneously by fission. Their study poses serious problems due to the following reason. First, in decay process, the emitted particles are extremely energetic, which break bonds and rupture crystal structure. The breaking of bonds by emitted particles in a sample of radioactive element is similar to the continuous self-reduction process. Therefore, it is difficult to prove the existence of oxidation state for every radioactive isotope. The energy given out appears largely as heat in the sample. For example, the heat produced by a millimolar solution of curium salt in water would be sufficient to evaporate the solution to dryness in a short time. The radioactive nature has two series operational consequences. First, because of the radioactive nature, it is necessary to employ elaborated radiation shielding, and therefore, in many cases, operations must be carried out by remote control. Second, the heavier elements have produced only in a very small amount. For example,